Sir, I would like to say the answer of the first question.
Yeah, go ahead.
Sir, under the influence of electric field, at first I want to explain what is drift current. Under the influence of electric field, hole will be moving. When the hole starts moving, we will find some current in there, and that is called drift current.
Yeah.
And in terms of diffusion current, uh, if we put a p-type semiconductor in a jar at a corner, it will spread throughout the jar
Yeah.
until it becomes uniform.
Okay.
That means the hole will move and we will get a current which is called diffusion current.
Okay, fine. So in regard to your definition of drift current and diffusion current, so what will happen to figure 1? So are we going to have any drift current or diffusion current? So that you have completed the drawing in figure 1. Are you going to see any drift current or diffusion current? Anyone?
Yes, sir.
Okay, why? Why would we see drift current and diffusion current in both type of semiconductors? So let's say this is our n-type semiconductor, let's say this is our p-type semiconductor. Why would you see a diffusion current here and a diffusion current here, or a drift current here, or a drift current here? Why?
Sir, under the influence of electric field, under the influence of electric field, the holes will start moving in a p-type semiconductor.
Yeah, but the question is, do we have an electric field here?
Sir, can I answer that?
Yeah, sure.
So if we place the, I mean, for example, the p-type semiconductor, if we place the p-type semiconductor under a electrical field, then
Yeah, but we don't have an electric field, do we? I said that
Sir,
in the current
oh,
is
so if we don't have an electric field there, I don't think there will be any drift
yeah,
current.
that's the thing. That's about it.
zero current.
So
Yes, sir.
we are all everything is under this present condition. In these conditions, what are we going to have? Are we going to have any drift current or diffusion current?
So
Or
No,
we won't have any
not
drift current.
have any current, sir,
so that means you are not going to have any diffusion current or drift
or
current
drift current.
uh, during this condition, because
Yes, sir.
we have, because if you consider it n-type material, so that means concentration of electron will be uniform throughout the semiconductor. Similarly, if you consider it's a p-type material, then you will find the concentration hole will be uniform throughout the semiconductor. So that means since there is no variation in concentration either in this n-type material or in this p-type material, we are not going to see any diffusion current inside n-type material or inside p-type material. So
Yes,
need
sir.
no diffusion currents. So in regards to drift current, for drift current to take place, we must have an electric field. However, we don't see any electric field. So therefore, when the semiconductors are isolated from each other and in equilibrium condition, we are not going to see any drift current and diffusion current. Is that all right? Is that explanation all right?
Yes, sir.
Yes, sir.
Thank you.
Yes, sir.
Okay, so this is our question 1. And the question 2, draw figure 2 by bringing these two semiconductor in contact with each other. So let's draw it. Okay. So let's say let's draw it this way simply. Let's make it p-type material by putting circle. So let's say this is our p-type material, and then we have our n-type material by, say that by drawing E. So this has become our n-type metal, p-type metal. Here hole is our majority carrier, minority carrier. So then we should have few minority carrier here. Let's say minority carrier, minority carrier. And then also we should have few majority carrier there. It's enough. So there is our p-type material and n-type material are brought in contact with each other, where so there is hole as majority carrier and electron is minority carrier, and there is electron as majority carrier and hole is minority carrier. So next we see what happens. Let's say we bring this. So this is our question 2. Okay. Question 3. Are you following me?
Yes, sir.
Yes, sir.
Okay. So sometimes little
Yes, sir.
noise would be helpful for me. Okay. So question 3. Show with the help of diagram how bound charges are exposed near the junction. Now we already learned that whenever you have a hole, so we have to imagine as if there is a, so that means you can say this negatively charged boron ion and this positively charged hole are neutralizing each other out. And for every hole, you have to imagine there must be a negatively charged boron ion. You just imagine that behind every hole there is a negatively charged boron ion. Okay, which we didn't draw it. Just we drew it for here. Similarly, what is going to happen for electron? For every electron, you see the thing that you don't see is there is a positively charged phosphorus ion. Similarly, for every electron, so positively charged phosphorus ion, so positively charged phosphorus ion. Now we learned that so boron ion, when you dope boron ion, when it accepts one electron from the neighboring bond, a hole is generated and boron becomes negatively charged ion. Similarly, when we add one phosphorus, the phosphorus donates its unused fifth electron. In the process, it becomes positively charged phosphorus ion. However, as long as the hole stays closer to the negatively charged boron ion, it remains, the whole region becomes neutral. So they neutralize each other. Positively charged hole and the negatively charged boron ion neutralize each other. Similarly, as long as the electron stays closer to the phosphorus ion, so they neutralize each other. So that is the scenario that we have got. And then we said that when we draw a p-type and n-type material, what happens is that since we can clearly see the concentration of hole on p site is very high compared to the concentration of hole in n site. So clearly you can see there are plenty of holes in p site and the numbers of holes in n site is quite low. Similarly, if you notice, the concentration of electron in n site is very high compared to the concentration of electron in p site. So clearly we have variation in concentration. So now we already learned that if there is a variation in concentration, what is going to happen? What is going to happen?
So
So
diffusion.
diffusion.
Diffusion. Okay. So we're going to have diffusion. So let's say this target, this particular hole will diffuse from here to here. Okay. Let's physically move it over there. So let's bring this hole over here. So what happened? Since the hole moved from p site to n site due to diffusion, because it wants to go from high concentration area to low concentration area. In the process, what it is, it moved away from the negatively charged boron site. So that means this hole is no longer available for the boron ion to neutralize it. So that means we have a negative charge exposed. And the p site. So then hole has entered into the n site. Now once the hole has entered into n site, it's going to enter, there's plenty of electrons around it. And we already learned when electron and hole meets, what happens? We have
EHP recombination.
EHP recombination. We have EHP. And we learned that EHP recombination leads to disappearance of both electron and hole from the seam. So that means you're going to find that this hole and electron, they will, this hole will be gone, this electron will be gone. At the same time, the hole is also gone because they neutralize so they disappear each other. Now, what happened to the positively charged?
So the phosphorus ion gets exposed.
Yeah, phosphorus ion is also exposed. Both of them are exposed. So this way we find a positive charge on near the junction of the n side and the negative charge near the junction of the p side. Now, if you allow these things to happen for few holes and few electrons going this and this, so eventually we're going to have a situation. So let's say we have some positive charge, a layer of positive charge, and it's a layer of negative charge. As we have a layer of positive and layer of negative charge, we're going to have an electric field. So that is the thing. That was question number 3. How show with the help of diagram how bound charges are exposed near the junction. This is how the bound charges are exposed. That means boron ion in p side and phosphorus ion in n side are exposed. Number 4 question was show how equilibrium is reached. Okay, so that's a very important question, how equilibrium is reached. So let's say initially only few hole has crossed the junction and only few electron has crossed the junction. So therefore we have a layer of positive charge here and a layer of negative charge here. So let's go to our next slide. So we can draw it here. So this is our junction. So let's say only few positive charge, negative charge, and there is some amount of electric field. Remember that we haven't reached the equilibrium yet. So that means the electric field here is not constant. Now, as soon as some electric field has established, so what we're going to notice, the hole that is on the p side will still try to go from p side to n side. Why? Because we already learned during the diffusion process, hole will continue to move from high concentration area to low concentration area for how long? As long as the concentration isn't uniform. তার মানে হচ্ছে যতক্ষণ পর্যন্ত লেফট হ্যান্ড সাইডের হোল কনসেন্ট্রেশন এন্ড রাইট হ্যান্ড সাইডের হোল কনসেন্ট্রেশন isn't uniform, ততক্ষণ পর্যন্ত the hole will diffuse from high concentration area to low concentration area. So only at the beginning only few holes is crossed. That means most of the holes are still on the p side. So which means there is a force acting on all the holes to diffuse from p side to n side. So let's call this hole. So let's say this particular hole is trying to cross the junction. So this hole is going to experience two force acting on that. So one of the force we call it Fd, the force due to diffusion. So this is the force that is experiencing on itself so that it goes from p side to n side so that the concentration becomes uniform. But at the same time, when the hole is trying to cross this region where there is a layer of positive charge and there is negative charge, so it comes under the influence of this electric field. So that means, let's say the hole is traveling, so trying to travel. Okay, so its hole is right now from here to here. So once the hole has entered into this region and going in this direction, the hole is experiencing another force acting on it, and this force is due to this electric field. And this force, we know that the hole being a positive charge always experience the force in the same direction as the electric field. So that means hole has two force acting on that. So one of the force, is this, we call it Fe, the force due to the electric field, and another force is force due to the diffusion. So initially, since the concentration of hole is very high on the left hand side and the concentration of hole is very low on the right hand side, also the electric field as a layer of positive charge and the layer of negative charge is not that thick, so the corresponding electric field is also quite small. So we can clearly say force due to the diffusion is much more bigger than the force due to the electric field. So if this is the case, what will happen? আপনারা বলেন।
So will it pass through?
The hole will anyway overcome the the barrier offered by this electric field. So the hole will pass through. Now we know that as soon as the hole moved over here, what we have? We have a negative charge exposed, and also we have a positive charge exposed. So that means the hole transfer, one more hole transfer leads to electric fields going up. And since the numbers of hole has decreased by 1, and the numbers of hole has decreased by 1 here, and numbers of hole has increased by 1 here, so force due to diffusion for the next, let's say then another hole is trying to cross the junction. So this after the hole after this one, when the second hole try to cross the junction, so it is going to experience slightly bigger force due to the diffusion, force due to the electric field, and slightly smaller force due to the diffusion. Still, we're going to find that the force due to the diffusion is more than the force due to the electric field. So that means this second hole as well will cross the junction. So if the hole crosses the junction, we have got a positive charge here and we have got a negative charge here, which means our electric field goes up. And for the third holes, so it is going to experience bigger force due to the electric field and smaller force due to the diffusion. So if you continue these things, we have a situation where what we're going to happen? We're going to see a situation where force due to the diffusion will be almost equal to force due to the electric field. So in that case, so let's say after doing many holes and electrons crossing this junction, and so we're going to have a situation where we have got an electric field, we call it E naught. At that situation, when this hole, so further hole try to cross the junction, because it is still try to maintain uniform concentration across the semiconductors, hole try to cross the junction from here to here, but as soon as it is trying to enter into the junction, since the force due to the electric field is almost equal to or slightly bigger than force due, so it will be bounced back. It will not be able to cross the junction. So no further. Similarly, it's going to happen for electron. So no further diffusion of electron and hole. So that is our equilibrium situation. So this is our equilibrium situation. So that means at that situation, there is no further diffusion of hole and no further diffusion of electrons are taking place from p side to n side and n side to p side. Is that all right?
Yes, sir.
Yes, sir.
Yes, sir.
Any question regarding this?
No, sir.
Okay. So next go to the second question. So next question. So fourth question was how equilibrium is reached. Why at equilibrium no electron hole can stay permanently inside the depletion region. So that's the question from one student as well. So let's say, so once an electric field has been established. Okay. So once an electric field has, so we have an electric field. An electric field is existing where there is an exposed positive charge and exposed negative charge. So we called it what? Depletion region. We already said that this is called depletion region. Why do you call it depletion region? Because you see on the p side of the depletion, it's all negative charge due to the exposed boron ion, and n side of the depletion is we have positive charge due to the exposed phosphorus ion. Why they are exposed? Because there is no holes here to neutralize the boron ion, or there is no electron here to neutralize the phosphorus ion. Okay, so that means this region is depleted of holes and electron. So that is why you call it depletion. Also, it is called space charge layer. Space charge layer. Okay. SCL. Now, if somehow if you want to bring any holes, for example, let's say you want to introduce a hole here. So you want to introduce a hole. Say you want to bring somewhere, you drop a hole here. So what is going to happen? As soon as you bring one hole here, so it's going to encounter what? An electric field. So electric field. So under this influence of this electric field, what will happen? This electric field will push the hole out of this region. So that means, or if you bring one electron, 3 electrons, As soon as you bring one electrons, this electric field will push the electron out of this region. So that means we cannot keep any holes and electrons permanently here. You see, I said the permanently. So that means you can have the holes and electrons going from n-side to p-side to n-side, but they cannot stay there permanently. So that is the okay. So fifth question was, how is that possible to reduce the depletion region width? Can anyone say?
Yes, sir. I can say, sir.
Yes, yeah.
Sir, by giving a reverse bias voltage, we can increase the depletion layer.
Yeah. And I could reduce it.
By, sir, giving forward bias voltage and external bias voltage, we can decrease the depletion region, sir.
Yeah, exactly. That's what it is. So let's say we have so, so we bring a positive terminal as a negative terminal. That means it is forward bias. So when you apply a forward bias voltage, what is going to happen is this hole will be pushed, because positive charge, they repel each other. So hole will be pushed. So as the hole is pushed, some of the hole will enter into the depletion region. Just few minutes back we said we cannot keep any electron and hole on its own, but we can force it to enter. So as soon as this particular holes has entered into the depletion region, now this hole has come closer to the negatively charged boron ion. So it means it is no longer exposed. So which means it become neutralized. This has become neutralized. This has become neutralized. So essentially, our neutral region has been extended. So that means our depletion region width becomes smaller. Similarly, when the negative charge is here, so we have plenty of electrons. So this sum of the electron will enter into the depletion region. So this electron is going to neutralize the positively charged phosphorus ion. Positively charged phosphorus. So this way our width will be reduced. So as the width is reduced, you notice as soon as the width is reduced, what happens to the electric field? Are you going to have the same electric field as we have during equilibrium, or smaller electric field?
Smaller.
Smaller, sir.
So if it is smaller electric field, what will happen? You see, is the charge balance,
Diffusion star.
at equilibrium we have FD equal to FE. Now since the electric field has become smaller, so what will happen? We have FD is again bigger
FT is much
bigger
bigger
than
than
FE. So that means the hole will start to diffuse again. Hole will diffuse from p side to n side. Electron will diffuse from n side to p side. We have our diffusion process started again, and that will come out from the external circuit. So this we are going to have a flow of current. And for reverse bias, so we do the opposite. So that means, so it's negative terminal and it's positive terminal. So in that case, if we erase this, it's so let's say, this. So when we have reverse bias, the hole will move in the opposite direction because hole will be attracted. So that means if this hole moves away, so we're going to see, so let's say this hole has moved away. So this hole is moved away, this hole is moved away, this hole is moved away. So that means since all of them go this direction, and it is going to expose more negatively charged boron ion. So that means our depletion region will becomes even bigger. Similarly, this electron will move towards the terminal, and we're going to see more phosphorus ion. So this way, our depletion region width becomes even bigger. Okay, so that is our reverse bias. Let's see, we have any other question? Yeah. So all the question has been pretty much covered.
Sir,
Is it all right?
Yes, sir.
sir, can you hear me?
Yeah, it's in lecture video. You said that reverse bias p-type is connected. Yeah, p-type is connected to negative terminal and is connected to positive terminal. Yeah, I did the same thing, isn't that? For reverse bias, p-type is connected to the negative terminal and type is connected to the positive terminal. Any other question? Any problem understanding the material? So how do you get minority electrons in n-type semiconductor? Question 5, someone wants the question 5 to be answered. Okay, so you said that why why at equilibrium no electron and hole can stay permanently inside the depletion region. So that's I have already explained. Okay, I'm going to explain it again. We said that at the depletion region, what we have an electric field, and for some reason, if you introduce a hole, so the hole will find itself under the influence of this electric field, and as it is under the influence of this electric field, it will be drifted. So that's, for example, it's, you can imagine, say, let's say, can you if you have a you have a ball, or or a stone in your hand, can you keep it floating in midair? Can you?
No, sir.
No, you cannot, because as soon as you leave, it will go down, right? Na? Because due to the gravity.
So, sir, basically because of the depletion layer, it happens, right, sir?
Yeah, depletion region. Because of the depletion region, not actually, not directly, because of the depletion region, it's going to have an electric field, and this electric field is not allow the electron and hole to stay there permanently. Same as gravity, electric field and gravity actually same, in terms of force wise. I cannot keep anything floating, because as soon as you leave, it will fall down. Similarly, as soon as if you bring any hole or electron inside the depletion region, inside the electric field region, it will go either direction. Okay, so that's the. And third question, it was that, okay, how can we have electrons? Very good question. I didn't mention it there. I expected that to find it out. So let's say we have an n-type material. N-type material. So we have an. So we know that in n-type material we're supposed to get electron. But the question is, how do we get hole? Can anyone give any idea? Can anyone care to? You see, remember one thing, although in n-type material, we may have generated electron by doping phosphorus. That means every time you add one phosphorus, we get one free electron. But you have to keep the material at certain temperature, let's say 300 Kelvin. So if you keep the material at 300 Kelvin, can you stop bond breaking?
No, sir.
So you cannot stop bond breaking. So that means somewhere else we're going to have bond breaking. Now, if you have a bond breaking, what do we have? So that means, so this is how we got holes in n-type material. Do you get that? So this is how, this is our minority carrier. So this is electron is our majority carrier and hole is our minority carrier. Similarly, in p-type material, so by adding boron, we get hole, but by bond breaking, we get electron. So the answer is minority carrier is due to minority carrier is due to bond breaking or thermal generation. ঠিক আছে?
Yes, sir.
Yes, sir.
Any other question? If you don't have any questions, we are nearly come to an end. All right, thank you for attending.
Thank you, sir.
Thank you, sir.
Thank you, sir.